So, my name is Nivedita, and today I will be talking about radiotrophic fungi. And you might ask, what are radiotrophic fungi? And a radiotrophic fungus is defined by its ability to harness energy from ionic radiation and convert it into chemical energy. And this is actually really cool. And this process is known as radiosynthesis. And what happens here is that instead, and it's quite similar to photosynthesis, as both forms use radiation as an energy source, except that instead of chlorophyll, radiotrophic fungi use melanin, which is the pigment that gives color to our eyes, skin, and hair. And melanin acts as an electron transfer agent between NADH and ferricyanide. The process of radiotrophic fungi, yeah. Sure, so it seems like these organisms are really cool, right? I mean, they are autotrophs in a way, but most of these fungi rely on other ways of getting sustenance on the side, as well as many of them are pathogens, parasites, and saprophytes. But still, these fungi are very important, just as cool as they are. And scientists have used them to do a lot of groundbreaking research in medicine and even in fields related to space, and that we will cover very soon. So in this presentation, I will be using two units known as the grays and the sieverts in order to measure radiation. Grays is an SI unit used to measure the amount of energy absorbed by an object divided by its mass, and sieverts are used to measure the health effects of a certain form of radiation, and they take into account a lot of different things, including the type, the tissues exposed, and how much energy could be absorbed, and that is the formula for calculating grays. So the first use for radiotrophic fungi is in medicine, and this is more through the fact that they are melanized. In order for radiotrophic fungi to perform radiosynthesis, chances are that their DNA will need ample protection from radiation. Not all fungi contain melanin, and not all melanin-containing fungi are radiotrophic fungi, as melanin is an extremely common pigment, even in the kingdom of fungi, just like it is in the animal kingdom. And we can see a lot of interesting genes that are involved with protection against radiation. In S. cerevisiae, which is also known as Baker's yeast, this model organism carries many genes related to radiation damage, and they're related to DNA repair, DNA recombination, chromosome stability, endocytosis, ubiquitin degradation, and transcription. And all of these are pretty basic genes. But the interesting thing is that S. cerevisiae is related, or at least very similar to this extremely resistant fungus. It's like very resistant to ionic radiation and UV radiation, and it is called Eumatis. The reason why this species is so tolerant to UV and ionic radiation could be because of the sheer efficiency of its DNA repair system, as it is a parasite that likes to feast on its host alive, and that would always prove useful. Many of these radiation resistance genes found in S. cerevisiae and Eumatus are actually quite similar to human genes, and this studying these genes could eventually lead to the development of many new radiation-based cancer therapies, as these fungi are very resistant to radiation. And another use for radiotrophic fungi is bioremediation. And radioactive waste is still a huge problem in many areas, such as damaged nuclear reactor sites in Fukushima and Chernobyl. An example of this can be seen through the common, and there are many species that would clean this up as they do absorb radiation, and one of these is the common woodland mushroom, G. glutinosus, which concentrates the radioactive isotope cesium-137 over 10,000 times more than normal, and that's why people were advised not to consume this type of mushroom after the Chernobyl fallout. Many scientists have been looking for ways to grow these types of mushrooms and other similar radiotrophic fungi that absorb radiation properly, and then they plan to grow them in these areas and then remove them once most of the radioactive waste has been absorbed by these plants. And finally, and probably the most interesting one, these radiotrophic fungi would be very important to space exploration eventually, mainly because of our problems with ionizing radiation, and this makes up a large part of the galactic cosmic radiation, and it includes alpha decay, beta decay, and gamma radiation as well. And as we probably know, gamma radiation is very deadly as it's strong enough to ionize atoms, and these include atoms in our DNA, so it can cause cancer and other terrible things. But the thing is, average people on Earth do get exposed to enough of this on a daily basis, around 6.2 millisieverts per year. But the average astronaut in the International Space Station is exposed to approximately 144 millisieverts, and just 1 year into a 3-year mission into Mars, a person would have already been exposed to 400 microsieverts of radiation. So the problem here is not that people are being exposed to this, but it's just that when astronauts go into space, they're exposed to very large amounts of it, and that is the danger. So the ISS is looking for a more effective shield for its ship and different spacecrafts, especially those going to Mars. And so if we truly want to explore Mars and further, we need to find a way to deal with all this excessive radiation, and it should not be too heavy as it reduces radiation, as in the density should be small enough, but at the same time, it should be extremely effective. And radiotrophic fungi actually do very well here, as you see that they are the second highest in terms of melanized fungus. So their mass attenuation coefficient is basically how effectively they can capture radiation while being trapped in really small areas, and that is second to Martian regolith, which and regolith is a inorganic soil that you will find on top of on a planet. And some experiments relating to passive radiation shielding and radiotopes involve this art involve see yeah, so we need to this would be the most effective, as it's more effective than things like steel and bismuth, which are also more expensive. And the ideal organism for this is C. sparospermum, as it produces its own melanin with little external assistance. And there are many other radiotrophic fungi that can't do this without a substrate, like C. neoformans, which needs a substrate known as L-dopa, which is a precursor to melanin. And this fungus, unlike many other radiotrophic fungi like C. neoformans and Dormanditis, it's not a pathogen or a parasite, while these are, so it'll be much safer to have this on board than these two or many others, as most radiotrophic fungi are parasites and pathogens. So a study had been done involving C. sparospermum, and it was placed in a constant radiation field of 0.05 milligrays per hour, and colony. It was just measured and studied for 15 days. So it was while observing these melanized cells, uh, people started to observe that as long as these fungi had melanin, it didn't even matter that if they didn't have enough resources, they would still grow quite rapidly, which shows uh, just how little they need to get the job done. In fact, these cells were able to get rid of radiation by around 2.17 plus or minus 0.35%, while forming only a 1.7 millimeter thick wall on the outside of the ISS. And estimates were taken to believe that around 21 centimeters of fungi would have been needed to successfully get rid of most of the ionizing radiation while going to Mars. And with the help of Martian regolith, as seen here, uh, only 9 centimeters of C. sparosperm would have been needed to effectively build a shield that would get rid of most of the ionizing radiation that would provide be dangerous to astronauts. So as we can see, so these are my sources, and as we can see, solutions to many of our most current problems can lie in very simple things like fungi. So always, look to Mother Nature for answers. So.